Yes, sir.
Okay. So to discuss this particular algorithmic strategy or algorithmic paradigm, we will take a one problem. The problem is line segments intersection problem. So this is not a difficult problem as such. We are given n line segments. In two-dimensional plane. Now we have to find out these intersection points. And we have to report them. So the line segments are given by means of their endpoints. And for sake of simplicity, we assume that these endpoints are distinct. I mean, what I mean by distinct actually is same endpoint is not endpoint of other segment like this. It's not possible. Okay. So like this situation is not there. There's one assumption we will make. Node 3, basically node 2 endpoints are same. Okay. Another thing is we assume that actually each intersection is defined by exactly two segments. That means node 3 segments are passing through same intersection, but this is also not possible. All of this is for sake of simplicity in the algorithm, but we can remove these assumptions, okay, without changing the complexity of the algorithm. Okay. So these are the cases which is not part of the our input. Of course, there are many possibilities are there. Okay, suppose the same intersection point may be a end point of this one possible. So all these complicated cases are we are excluding. So we are assuming that these endpoints of this n line segment, what is given to us, they are distinct, and two line segments, okay, intersect at given point. Okay, each intersection point exactly defined by two segments. Okay, so this is the problem. So how anybody will solve this one? Very simple. Yeah, whoever is talking.
So simply take two lines and find the intersection of them. Finding intersection would take order.
Yeah, everybody able to hear? Hello? Everybody
Sir,
able to hear?
sir, like, what is, we need to only count the number of intersections or the points also, like the location of points also?
Yeah, we have to find out the intersection point and report it.
Okay.
Okay. Yeah, this is a good question actually. In geometry, there are two types of queries will be there. One is here, we want to report these intersection points. Another thing is count how many intersections are there. Okay. One is counting query, find out how many intersections are there. Another thing is reporting query. So report all the intersection point between these line segments. Reporting queries and counting query. So here we are looking at the reporting situation. So if you go back to your first year CS 101 course, okay, simple brute force method, you can take it. Okay, you take each segment and check against each and every other line segment. If they're intersecting, you report it. So basically what we have actually odd n square time algorithm. Okay. And if you look at carefully, and given line segments may have odd n square intersections possible. Okay. Simple one is you take n by 2 horizontal lines and n by 2 vertical lines. So you have odd n square intersections are there. So this complexity is tight. But in many cases, such a large number of intersections, worst case number of intersections are actually very unlikely. If you take any practical situation, intersection will be a few. For example, this problem comes in the geographical information system. I told in the introduction actually. So geographical information system is, okay, geographical information of any region. Okay. So geographical region means there are many things will be there: road network, rail network, river network, okay, or forest area coverage, okay, crop coverage, or maybe a terrain coverage. There are many things may possible. So one problem in geographical information system is we call it JAS. To take a two overlays, say for example, road network and river network, okay, and find out the intersection between them. Basically, where are the bridges are there, you want to identify from this one. The two information what is given to us, road network and river network. So basically, to find out where are the bridges are there, you have to find out the intersection between these two overlays. So road network or a river network, these can be approximated as a line segments. So if you want to find out intersection between the line segments, there are very few intersections will be there. But if you look at this number of line segments in each overlay, the large number of line segments will be there. Okay, so using a brute force method is a very inefficient thing. So is it possible to get a better algorithm? So this is the question. Is it clear to everyone? Any questions? Okay. See, if you want to check intersection between each and every pair of line segments, then complexity becomes odd n square. There's no alternate. So only thing, if you want to have a better algorithm than odd n square, we have to avoid checking the intersection between some line segments which are not likely to intersect. Okay. So that is the only way to get a better than odd n square algorithm. So which ways we can avoid checking? Line segments which are far away from each other. Maybe you don't need to check whether they're intersecting or not. That intuitively I'm telling. Okay. Is that clear? Yeah, everybody is able to hear me?
Yes, sir.
Yes, sir.
So any questions till now? So we don't want to check every pair of line segments for their intersection. So that is our target. To avoid some pairs intersecting or not, to check that one, so we can avoid pairs, okay, the line segments which are far away from each other. So that is our idea. Now, how to capture these line segments are far away so that we can avoid checking their intersection. Our input, in other words, we have to check line segments which are close to each other so that we can, there are potential intersection possible. So something which is close to each other, so maybe we can check for the intersection. So this is the idea. So if you come to this closeness, suppose two line segments you take. And take their X projection. Okay. So the X projection is overlapping. Okay. So we can capture this two line segment close to each other, means at least they, well, one way actually there maybe their X intersection, X projection is overlapping. Similarly, you can also see their Y projection. So they are overlapping. Of course, there could be a two line segment with their X overlap is there, Y overlap is there, but they are not intersecting. If they are intersecting and their X overlap, X is overlapping and Y also overlapping is there. Okay, but some are not intersecting, which are far away from each other, so there won't be any overlap actually. So this is one crude way of thinking. Of course, there are many different ways one can quantify closeness, but this is one crude way. Just we are looking at one-dimensional aspect of this line segments. Everybody following what I'm saying?
Yes, sir.
Okay. So okay, this is one point. Another point is here we want to have a better than odd n square algorithm. What do you mean by better square odd n square? Better than odd n square. See, only possibility is, see, in worst case, the complex is odd n square. There could be odd n square intersections are possible. Okay, we cannot have a better than odd n square algorithm. But we can have output sensitive algorithm. Maybe something like this. Here K may be a number of intersection points, or maybe something like this. So if the number of intersections are low, okay, then these are better algorithms than odd n square. So here we are trying to obtain a one output sensitive algorithm. Okay. Now we made an observation that there should be a X overlap and Y overlap should be there for the two intersecting line segments. So now question is how to capture this X intercept and Y intercept, not X overlap and Y overlap. Okay. So for that actually, so this is what is called a the sweep line algorithm is what is proposed. So what is the sweep line algorithm? Yeah, take this example here. So we assume that there is an imaginary line, like a horizontal line, and sweeping the plane from top to bottom. So there is a horizontal, infinite horizontal line is there. And visualize that this horizontal line is sweeping the plane from top to bottom. So whenever it sweeps, okay, suppose during the sweep, and suppose assume that this sweep line is reached this position. That means from here to here, it covered from the top to the current position. So in the process, it actually crossed all these intersection points. So we want to report all the intersection points which are crossed by this sweep line status. That means whenever this sweep line is crossing some intersection point, it has to report. Okay. Yeah. So how to do this one? This is an imaginary line. So what we will do actually, we will maintain a one data structure to represent the current state of the sweep line. Okay. What does it mean by this one? Okay. Let's come to here. Let's take a few line segments. Let's take a sweep line and this one. So let's name them actually. This is say S1, S2, 3, 4, and say this is S5, S6. So we are sweeping the plane from top to bottom using a horizontal sweep line. And what we will do actually, we'll represent this sweep line, current position of the sweep line, by means of these segments which are intersected by the sweep line. Okay, at this position, this is intersecting S1, S2, S3, S4, and we'll maintain these segments as a part of the sweep line status. When the sweep line is here, the sweep line status is S6, S7, and S9. Okay, when the sweep line is here, the sweep line status is S9. So we are visualizing this imaginary horizontal line is sweeping from the top to bottom, but as a computationally or algorithmically, we are keeping the set of line segments which are intersected by the sweep line at current position as its status. So this is what is called a sweep line status. Okay, the sweep line status. So you have to remember one thing. See, we are not representing these intersection points as a part of the sweep line status. I mean, intersection between the current position of the sweep line and the segments. We are not representing the sweep line status as these intersection points. Why? Because when the sweep line moves, these intersection points are changing. So that means whenever this moving continuously from top to bottom, these intersection points are continuously changing. It is not possible to maintain these intersection points as a in any form, anything actually. So instead of that, what we will keep actually is set of line segments which are intersected by the current sweep line, current position of the sweep line. Okay, so that's why we are keeping the segments in the sweep line status, not the intersection points. That means at current position of the sweep line, so this sweep line is intersecting these segments. And another thing is, this set of segments which are intersected by the sweep line, we maintain them left to right order. So this is the way I written there. Okay, left to right order. Okay. So this is what is called a sweep line status. So don't worry about the data structure, what data structure actually represented. But here we are representing the sweep line status as a set of line segments intersected by the sweep line from left to right order. There will be some data structure which represent this one. This is one point. And second point is, when the sweep line changes from top to bottom, then sweep line status changes. See, for example, for this sweep line status and this sweep line status, there is a change is there. Similarly, to this one, there is a change is there. So sweep line status changing. Is it changing continuously, or it changing at some finite points? Yeah, anybody can answer?
So they change at the ends of the line segments.
Okay, anywhere else?
Intersection points.
Yeah, so that's true. The sweep line status changes at top end point of a line segment, bottom end point of a line segment, and intersection point also. Okay, let's look at it. So right now sweep line is here. There are some segments are there already. So let's name them 1, 2, 3. So sweep line status here is S1, S3, and S2. Suppose, yeah, this is the new segment here. Say this is the S4. Whenever it crosses the top end point of a segment S4, then the status is changed to agree. Yeah, let's extend this to line a little further. Okay. And similarly, bottom end point. Whenever it crosses the bottom end point, and then status is changed to S1, S4, and S3. So basically what happened, the S4 is inserted into the sweep line status whenever it crosses the top end point, and whenever it crosses the bottom point, you have to remove that segment from the sweep line status. Okay. Insert and delete. Similarly, whenever it crosses intersection point. So here status is S1, S2, S3, S4. Now here S1, S3, S2, S4. So sweep lane status is changed here. So those are intersecting at this one, their order is changed. Okay. So these are the three different types of events where status of the sweep lane status changes. Okay. Top end point, bottom end point, intersection point. These are the different types of events where sweep lane status changes. Of course, whenever the line segments are given, we know the top end points and bottom end points of these segments. Okay, we know these events beforehand. Of course, we don't know these intersection points. Of course, our aim is to find these intersection points. Okay, so in the process of the sweeping from the top to bottom, on the fly, we compute the intersection points and we use them to updating the sweep lane status as well as reporting. Okay, so here we are talking about two things. One is the sweep lane status. We need some data structure to represent sweep lane status. Okay, and we need another data structure to represent the events, event Q. Why Q? Because we want to process these events from the top to bottom. Whenever sweep lane crosses any event, we want to update its status. Okay, so we are processing these events from top to bottom order. So that's why we maintain an event queue. So we need two data structures. So any questions till now? So any questions? No. Are you listening?
Yes, sir.
Yes, sir.
Okay. Now, see, we don't bother about this data structure and time complex as of now. So we simply look at this algorithm. What we'll do, we will initialize this sweep lane status with T and event Q. Okay. Bottom order of endpoints of segments. So while Q is not empty, what do you do? So extract the, because these events are there in the queue and we want to process from the top to bottom. Okay. So we extracted the first one. Suppose if it is a okay, whenever this we extract one is, suppose if it's a top end point of segment SI, then what we will do? So simply insert into the sweep length status. Okay. Now, okay. So just not inserting, actually we have to do something more also. Suppose if this is the sweep length status and you have, these are the segments and we are inserting the segment here. Say this is the S1 and S2 and say S3. Now sweep length status before this event is S1, S2 and after this one is S1, S3, S2. Okay. So after inserting the S3 into the sweep length status, we have to check this new segment intersecting the adjacent line segments or not. Adjacent line segment means adjacent in the sweep length status. So when you are identified, you are inserting this between S1 and S2, you know that S1 and S2, which are either side of this S3. So you check whether this S3 is intersecting with S1 or not. Okay. Similarly, check whether S3 is intersecting with S2 or not. If they are intersecting, find the intersection point and insert into the event queue. Why we have to do this one? By inserting this segment S3 into the sweep length status, S1 and S3 becoming a adjacent here. Similarly, S3 and S2 are becoming adjacent to each other. What does it mean actually? If you take a Y projection of these segments, there is an overlap between the S1 and S3 and S3 and S2. So we check whether they are intersecting or not. They may intersect, they may not intersect, we don't know. But we'll check that. Okay. So everybody is following what I'm saying?
Yes, sir.
Sir, I have a doubt, sir.
Yeah.
Sir, you're telling whenever we are inserting, if they will be intersecting at the time of insertion, they will be adjacent inside the status.
Say it again.
What I understood was that whenever we are inserting a point, we'll be checking, and then you told that these are adjacent over here. So is this a general conclusion that whenever we are inserting a point, then if the line is intersecting with some other line, then it will be adjacent to this one?
No, you're saying two different things. Okay. Yeah, I will say what I want to say here. Whenever two line segments intersect each other, they become adjacent to each other in the sweep plane status before intersection. Agree?
Yes,
So
sir.
before this intersection, S1 and S3 are adjacent to each other in the sweep plane status. Okay. Similarly, S2 and S3 also adjacent to each other, but they're not intersecting. So two segments adjacent to each other may lead to intersection point, may not lead to intersection point. But if two segments are intersecting each other, means those two becomes adjacent to each other before they intersect.
Yes, sir. I got it now.
So before, after, in the sense actually we are sweeping from top to bottom in that direction, in that order. So we don't know which segments are overlapping, which are not which are intersecting, which are not intersecting. But whenever the new adjacency is formed, like here S1 and S3, S3 and S2, we'll check whether this new adjacency is leading to a new intersection point or not. If it is leading to a new intersection point, find out that intersection point and insert into event queue. If it is not leading to a intersection point, do nothing. Okay, but at least you have to check. Okay, is that clear?
Yes, sir. It's clear now, sir.
I write the procedure. So I write the procedure here. Okay, if SI and SL. Okay, so since this SL is the left of the SI and SR is the right of SI. Okay, so you check whether SI and SL are intersecting or not. If they're intersecting, find out the intersection and insert into event queue. If not, you do nothing. Similarly, you do the same thing for SI and SR also. Then find intersection point. Okay, is that clear? These are the steps we have to execute whenever the sweep lane status crosses the top end point.
Sir, I have a question here.
Yes.
What happens if there is a line parallel to the sweep line?
Okay. Yeah, this is a good question. So as of now, assume that there's no any horizontal lines as of now.
Okay.
Okay. These are only for sake of simplicity in understanding algorithm. So once you understand the algorithm, all these assumptions can be removed one after other without violating the time complexity. Okay. So any questions here? Okay. Now, if this is the action need to be taken at the top end point. Similarly, if it is a bottom end point, So look at here. We have sweep line here. We have some line segments are there. So this is going out of the sweep line status. So this is SL and SR. So before this sweep line set, before crossing this bottom end point, and this is the sweep line status. After this, this is the sweep line status. Okay. So basically, we have to remove this SI. Okay. Not only just removing the SI, now this SL and SR becoming adjacent to each other after this removing this SI. So there is a new adjacency pair is formed. So whenever the new adjacency pair is formed, you check whether they're intersecting or not. So of course, in this diagram, they're not intersecting, but there is a possibility that they may intersect like this. So since we are removing the SI and SL and SR becoming a new adjacent pairs in the sweep line status, so you check whether there is a intersection is there or not between them. If there is intersection point, and find out, insert into the event queue. So this is the action need to be taken. So what are things you have to do it? You find out what is there on the left of left of SI in L, and SR is the right of SI in L. Okay, and delete SI from L. Then you check if SL and SR intersecting. Then find out intersection. Between this SL and SR and insert this intersection point into event queue. Okay, is that clear? Any questions? Don't worry about the data structures, the operation to perform, and complex algorithm. We'll work out all those things. Yeah, not today, maybe next class. Okay. Now, third type of event. The sweep line status is changed to so the order of these segments are changed in the sweep line status. Okay, this updation is to be done, and there is a new adjacent pair is formed. So we have to check whether they are intersecting or not. If they are intersecting, find the intersection and set into the event queue. Okay. So here we assume that actually is left of Sj, okay, in sweepment status. We have to find out which one is left of the, which one is right in the sweepment status. But we know that this Q is, that the event Q is actually intersection between Si and Sj, that we know. Then which we have to find out which one is left and which one is right in the sweepment status. So once we have identified this one, okay, find out the left of Si in L and find out the right of Si in L. So you check if this is the SL and this is the SR, okay? So you check whether this SL and Sj are intersecting. Then find intersection between SL and Sj and insert, okay, this into the event queue. Similarly, do the same thing for Sj. I'm just skipping this. Okay. Now, what are things to be done? Update this Si and Sj, okay, in L actually. This I'm writing this in short actually. Basically, you have to swap the position of Si and Sj, okay. Then output Q. So you have to report Q as an intersection point. This is the action need to be taken whenever this event Q is crosses the intersection point. Any questions till now?
Sir, here the SL is the left of Si and the SR is the right of Sj, right?
SL is the left of Si and SR is the right of Sj. Yes. Yeah, this is J. You got it? Now,
Yes, sir.
yeah, we don't have much time. I will tell complexity here. Again, we discuss this once again. Okay. Next class. Now assume all these steps takes a logarithmic time. Log of size of L. What is the size of L possible? L is the all the line segment intersected by the sweep length status. So it may intersect all of them. Size is at most n. So it's log n. Okay. And finding the intersection point and inserting this is, okay, again logarithmic time, log of size of Q. So what is the size of Q? Number of events. So number of events, top end points are n, bottom end points are n, and intersection points. So there can be any number. So in worst case, out n square. So log of n square. So this log n. Okay. So here we are doing a amortized time complexity analysis here. So to process one top end point, we need a log n time. Okay. And log n time to update this event queue. So all of them is log n. So we are having a n top endpoints. Total time complexity to process all the top endpoints are n log n. So each top endpoint takes a logarithmic time. There are n top endpoints are there, and log n is time complexity. So everybody agreed with this one? Yes. Of course, we have to find out a suitable data structure. All this can be done logarithmic time. Okay. Similarly, you have to find a suitable data structure for the sequence setters and event queue so that these operations can be logarithmic. It's practically possible. You can think of. Okay. Okay. Assume that there is a data structure to do all these things in logarithmic time. Similarly, bottom endpoint, finding the leftmost, rightmost, and this again logarithmic time. Okay, inserting also logarithmic time. So this is also takes n log n time. Now come back to this intersection points. So again, this is a logarithmic time, all these things steps, and just all our logarithmic time output it. So if there are intersection points are k, so k log n is the time. So overall time complexity is k n plus k log n. Okay. Any questions? And I'll mention one thing. You required a height balanced binary history for the L and priority queue data structure for the Q. These two are sufficient to perform all these operations logarithmic time. Okay, nothing more is required. Height balanced binary history and event queue. Heap, binary heap is sufficient. So to perform this one, simple data structure is sufficient here. So all of you go through this algorithm. So this I'm discussing from the computational geometry algorithms and application by Deberg and Van Kerveld and Warmarsh. Okay. So from this book, I think this is second chapter. This is the sweeping algorithm. This paradigm is unique to the geometric algorithms. Okay. So, and this is a very nice paradigm. We can solve large number of problems. Okay. So we'll continue next class. So don't forget to fill your group information. Otherwise, tomorrow we will form a arbitrary we assign. Okay. So see you next class.